Great. Thanks so much for that. Hi, I'm Genevieve. Today I'll be presenting a study that I recently completed. I'll briefly introduce driving hazard perception, how hazard perception skills are acquired and how they can be trained, and also the effects of TDCS on learning. So driving hazard perception is defined as the ability to recognize and respond to traffic hazards. It predicts retrospective and prospective crash risk, meaning that drivers who are slower to recognize and respond to traffic hazards are more likely to be involved in a crash. A fact sheet put together in 2006 by the Queensland Government Department of Transport and Main Roads found that drivers aged 16 to 25 years are 60% more likely to be involved in a serious or fatal crash as compared to any other age group. And this statistic has changed very little over the following decade or so, where young drivers account for more than 20% of the driver or motorbike rider fatality in 2015, but they only represent 13.8% of the licensed driver population. A driver's crash risk tends to reduce the more on-road driving experience they accumulate, but developing a high level of hazard perception skill can take up to 30 years of regular on-road driving, and waiting for a novice driver to accumulate experience over the years does very little to reduce their crash risk right now. So how can we improve hazard perception? So good hazard perception skills are typically conceptualized as good situational awareness, whereby experienced drivers develop a sophisticated mental representation of the driving environment over time. This means that experienced drivers are better at processing the visual environment and are more aware of cues that predict a potential hazard. And novice drivers, on the other hand, are unlikely to have the experience required to predict the behaviors of other road users. Thus, hazard perception skill develops slowly over time, but it has been demonstrated that training interventions can speed up hazard perception skill acquisition, where significant training effects have been observed in both novice drivers and experienced older drivers. However, could there be other methods to improve hazard perception? One method of improving performance is to non-invasively stimulate the brain, and non-invasive brain stimulation can be used to modulate neurocognitive abilities by using small electrical currents or magnetic pulses to directly alter brain activity in a safe and painless way. In my study, I've chosen to use transcranial direct current stimulation, or TDCS, and broadly speaking, there are two main mechanisms by which TDCS works. Typically, anodal stimulation induces excitatory effects in the underlying cortex, and cathodal stimulation induces inhibitory effects. Previous studies have demonstrated the ability of TDCS to modulate performance on visual, cognitive, and motor tasks, including the enhancement of attention, learning, and memory processes in healthy adults. This may have potential stimulation effects on other higher order processes that underlie hazard perception. Examples include executive functioning, decision-making processes, and risk-taking propensity. So the aim of my study was to investigate how TDCS can modulate hazard perception skill acquisition in novice drivers aged 18 to 25 years old who are undergoing a hazard perception intervention. So I hypothesized that with pre-intervention scores as a covariate, we predict that at post-intervention, participants who receive anodal TDCS applied to the bilateral DLPFC will demonstrate faster response times and increased accuracy in detecting potential hazards on a hazard perception test, as compared to participants who receive sham TDCS. So this is the design and methodology of my study. I recruited 40 participants in a between participant design, and participants were randomly assigned to receive either the active stimulation or the sham stimulation. So all participants first completed a hazard perception test with the test order counterbalanced between the first session and the last session, and the video order randomized to prevent practice effects. Then they completed 3 sessions of a hazard perception training intervention developed by my supervisor, Professor Mark Oswell, and colleagues in 2016. Each session was approximately 1 hour long, spaced a week apart, and participants received TDCS whilst completing the training intervention. The stimulation protocol was 3 blocks of 15 minutes of continuous stimulation at 2 milliamps, with a 60-second ramp-up time to reduce the physical tingling sensation that some participants experienced. And the active stimulation included bilateral anodal stimulation to the left and right DLPFC, located on the F3 and F4 positions on the international 1020 system, and the reference electrode was placed on the back of the participant's neck. For the sham stimulation, we used an active sham protocol where the anodal electrodes were placed in the same place as the active stimulation, but the cathodal electrode was placed on the top of the head and in between the anodal electrodes in the approximate CZ location. This encourages the electrical current to shunt from the electrode directly to the cathode without passing through the brain at all. And this method has been demonstrated to be an effective sham method as participants experience the same physical sensations without the actual brain stimulation. And the dependent variables were reaction time in seconds from the onset of a hazard to a response by mouse click, and also the accuracy of hazard identification measured in percent correctly identified. So in each session, participants viewed 95 scenes of driving footage and were instructed to click on a potential hazard when they identified one. So these are the results of the 40 participants. We did a one-way encover, and we found no significant response time differences between the sham and active conditions. So if you look at the graph, you will see that on the y-axis, it is the standardized reaction time, and the x-axis is the simulation condition, and there is no significant difference between them. We conducted Bayesian statistics as well, which also indicated support for the null hypothesis where there was no effect. For accuracy, we also found no significant response time differences between sham and active conditions. And this was also similar when we conducted Bayesian statistics. So more support for the null hypothesis. And so in conclusion, the results indicated no facilitative effects of active stimulation for this hazard perception training intervention. Possible explanations for the null effect include potential dosage effects, perhaps 2 milliamps was too high, or limitations in the spatial specificity of TBCS in general. It could be that the brain regions responsible for hazard perception skill acquisition were not sufficiently stimulated. There could be insufficient time or too few sessions. We only stimulated participants over 3 sessions. Hazard perception is a skill that takes years to acquire, and therefore neural substrates could require more time to consolidate the information learned. And finally, this is the first study to investigate the effects of non-invasive brain stimulation on a complex higher order task, such as learning hazard perception. So there are still much more avenues for exploration. And thank you. Thank you so much.
Thank you, Genevieve. Thank you for the clear presentation. Now, I've got a quick question. So you used the bilateral stimulation.
Yeah.
Have you considered different montage, say, for example, just a single, not a bilateral, just a single normal montage? And what is the implication if you are to use a different the montage?
Yeah, so we used the bilateral montage primarily because we wanted to stimulate both sides, where most of the literature indicated that the left DLPFC was mainly focused on executive functioning, and the right DLPFC was more of the risk-taking propensity. So we thought if we stimulated both of them, there could be an effect, but there is definitely the opportunity to stimulate just one side, see if there is more of an effect of, say, executive functioning from the left or risk-taking from the right. But yeah, that's definitely an avenue for future research.
Okay, thank you. Just one more follow-up question. So you mentioned that, for the future or implication or sort of limitation, the 2 milliampere could have been a bit too strong for some people, or it could have been a bit too weak for other some participants as well. So maybe, some more individual kind of, adjusted the parameters could be resulted in interesting results or expected results.
Yeah, definitely. So this is the first study of its kind. So I just kind of chose 2 milliamps to see where it kind of led us. But I have also read other research papers, not specifically on hazard perception, but more of cognitive functions and executive functioning, decision making, etc. And they have found that there are different effects at different intensities of stimulation. So it could be that 1 milliamp may be good, or 1.5 milliamps. Haven't really read very much about going more than 2 milliamps. That may be a bit too intense for in terms of the physical sensations, but it could be an option to investigate.
Great.
Yeah.
Okay, thank you. Now, there's a question from Kate. So did you control for between group baseline differences?
On the hazard perception test?
I assume so.
Well, yes, yes, we did. So there was no between group differences in terms of the hazard perception test scores at baseline.
Okay, excellent. Thank you so much for your presentation.